All right, last year in Science 10, okay, you learned about acceleration. Okay? And what you basically learned, essentially the definition of acceleration, is still something that's really important. You'd be surprised how often an understanding of what it means to accelerate comes up in this course. Okay? Not just in Unit 1, but especially in Units 2 and 3, okay, where objects are undergoing forces that are causing acceleration. So the nature of acceleration is a topic that comes up a lot in Physics 20 and in Physics 30. Okay? So, as a quick review, okay, the definition of acceleration is any change in velocity over time. Okay? So anytime an object's velocity is changing, it is by definition accelerating, even if it's slowing down. Okay? The word accelerate, okay, does not connotate direction. Acceleration is any change in direction, or change in velocity. Okay? It's any change in velocity, right? Whether that's a negative change or a positive change, the object is changing its velocity, so that's acceleration. Okay? All right, and the big thing to remember about this, okay, is that the definition says change in velocity. Okay? When we get into Unit 3, there'll come this point where we'll be talking about an object that's accelerating, but traveling at a constant speed. It's possible. Okay? If an object is moving around and around in a circle, okay, that requires the object to be accelerating, but it can do it at a constant speed. Only its direction is changing. Velocity is a vector quantity, so even if it's just the direction that's changing, okay, it still counts as a change in velocity because velocity is a vector quantity. Okay, so that's why you don't see the word speed in the definition. All right. Right, so whenever the velocity of an object is changing, velocity of an object, not speed. Velocity of an object is changing, we say the object is accelerating. Okay, and that can be only a change in direction. The magnitude of the velocity can actually stay the same, and the object would still be accelerating because it is turning. Okay, if you don't believe me, think back to any of the number of times somebody has ended up putting their car or truck in the pond out here. Okay, if you take that corner too fast when it is icy, you do not produce an acceleration by turning your wheels. You travel at a constant speed into the drink. Okay? And it happens. Every year somebody ends up in that pond. All right? If you manage to produce an acceleration by A, not going too fast, and B, not turning too sharp, okay, then you actually are able to accelerate even if your speedometer, which measures speed, doesn't change as you go around the corner. Okay? You're changing direction, that's an acceleration. Okay? Friction is required for that to happen. Okay, so what we learned last year about acceleration is this. Okay? That acceleration is a change in velocity over time. So A equals final velocity minus initial velocity divided by time. Okay? Can we plug speed in there if we're given different changes in speed? We absolutely can. It works. Okay? We're just saying that the definition only involves the word velocity. Okay, everybody all right with that idea? Hey, like I said, you'd just be surprised how often having an understanding of the definition of acceleration comes up. All right? Now, where did we get this formula from? Don't say my formula sheet, if you were thinking that. It's on there, but that's not where it came from. Okay? Remember that this formula, A equals VF minus VI over T, is the slope of a line on a velocity versus time graph. Okay, so if I got this graph and I got the equation and it was like that, okay, the acceleration of that object would be what would it be? Garrett, what would it be?
3.27.
Absolutely. The slope of the line, 3.27. What are my units for acceleration?
Meters per second.
Meters per second squared. Meters per second, right? It's how quickly I'm changing my velocity. Velocity is in meters per second. I'm dividing that by time, meters per second, okay? Which we always say is meters per second squared. Okay, so the slope of this line is the acceleration, because if I solve for this number, if I do this, okay, y would be any value on the line. It would be my final velocity. B is the velocity at time 0. By definition, that would be its initial velocity. And x is time. Okay, so really, this formula is Vf minus Vi over t. Okay, that's where that formula comes from. Okay. Everybody with me there? All right, so this would be a question like you would have got right at the very beginning of acceleration in Science 10. All right, so we have a plane, and at time 0, its velocity is 0. Now, in this question, it says it starts from rest. Okay? If you are at rest, what are you not doing? Yeah, you said it. Moving. Okay? If you are at rest, you are not moving. By definition, then, your velocity is 0. So if something starts from rest, Vi is 0. What if the object comes to rest? Nice. Vf is 0 in that situation. If it comes to rest, that means it's slowing down, and eventually its velocity is 0. Okay? That makes Vf 0 in that situation. Always be on the lookout for the word rest. Okay? If it's starting from rest, it's talking about Vi being 0. If it's coming to rest, it's talking about Vf being 0. It's just one of those terms that you have to be on the lookout for. All right, so in this situation here, we know that Vi is 0 meters per second. Okay? The plane accelerates down the runway, and 29 seconds later, okay, it is moving at positive 72.2. That would be Vf then. Okay, what would the acceleration of the plane be? Okay, so A equals Vf minus Vi over t. We have all of those numbers, so it's just a matter of plugging them in. So 72.2 minus 0, okay, divided by 29 seconds. Okay, if we do that, okay, I don't remember what that comes out to, but it's probably on the next page. 2.5 meters per second squared, and it's positive because it's going faster in a forward direction. Okay? Acceleration is a vector quantity. Okay? Super important to remember that. Okay? The number one thing I see people forget in an acceleration problem is vectors. They just outright, for whatever reason, ignore them. Okay? You cannot. Right? We're talking about velocity, a change in velocity, that's vector. Acceleration is vector. Okay? Everybody all right with that? Okay, is that ringing a bell from last year in Science 10? Okay, here are the other acceleration formulas that we are going to be using in this course. They are all on your formula sheet. So you're going to want to have that out a lot over the next few days because we're going to be using it a lot. Okay? Now, they don't all solve for A. A is in them, you can manipulate it to solve for A, but they don't all start out that way. Okay? These two come from the same place. In fact, we talked about one of them the other day when we were talking about finding the area between the line and the x-axis on a velocity versus time graph. Okay? So, here's where these two formulas come from. If I have a velocity versus time graph that looks like this, so just like the one I just had, okay, so this is meters per second and this is seconds. If I wanted to calculate the total displacement of this object, I would find the area under this line. Agreed? Would that be fair? Okay, so that would mean calculating this rectangle and that triangle. Okay, so would the area of this rectangle be my initial velocity times the time? Right? Base time times height, VI. Everybody okay with that idea? Okay, so this calculates the area of the rectangle, right? And then when I calculate the area of this triangle, okay, what we usually do is we go base, so the time, times the height divided by 2. When I divide the height by 2, what I'm really doing is this. Okay, so if I've got y equals m times x plus b, I know that this is my acceleration here. Okay, so if I want to find the height of this triangle, what I end up doing is I end up multiplying m times x, so acceleration times time, okay, and then okay, I divide it by 2. So I end up getting this at squared here, okay, to calculate the area of the triangle. Okay? Everybody with me there? So here's why that works. I go m times x, that gets me the height of the triangle. Then I got to go height times the base, so I'm multiplying it by x again, and then dividing by time. So what I'm really doing is going acceleration times time divided by 2. Is that acceleration times time squared divided by 2? Okay. Is that exactly what 1/2 at squared would calculate? Okay, so that calculates, that's where this formula comes from. It calculates the area between the line and the x-axis. That's why it works. That can be handy on the lab we're going to do on Wednesday. That formula can be pretty handy. Okay, so I don't know if you want to make a note of that somewhere. Handy for Wednesday's lab. I don't know. All right, this one is the opposite. Okay? Instead of using the initial velocity, it takes the final velocity and multiplies it by time. So I'm just going to draw that graph again here. Okay, so it's using the final velocity here, okay, so this value here, and it's multiplying it by the time. If I do that, I'm calculating the area of this entire box. Would you agree? Final velocity times time would be base times height for that box. Then it subtracts 1/2 at squared. The other formula added it. Well, the reason this formula is subtracting it is because this triangle here and this triangle here are equal. So by taking this whole box and subtracting this triangle, does that leave me with what I wanted? Are they calculating the same thing? Okay. They're calculating the displacement either way. Okay. They're finding that area between the line and the x-axis. Okay. Either formula is doing that. One just has the ability to use VF, and the other has the ability to use VI. It comes in handy if you're only given one or the other. All right, this one here, okay, we won't talk about the derivation of this one, but it does come in handy a lot in projectile motion. Okay, notice that that one doesn't involve time. Okay, that one can help you get acceleration without knowing how long the object is accelerating for, just knowing how far it goes. Okay, instead, so that one can be pretty useful if you're not given time. And then there's this one. We don't use the last one very often. Okay? And the reason we don't use it very often is because it can only work if the question outright states that the acceleration is uniform. Okay? And the reason for that is, I'm just going to rewrite this so it looks a little bit different. D equals VF plus VI divided by 2. Okay? If I add two things together and then divide by 2, what am I calculating? I'm calculating the average. So is this formula, since it's multiplied by t, really just saying this? Is it really just D equals V times T? Okay. It absolutely is. So we don't use it as often because if it's not perfectly uniform, it doesn't work. Okay? There will be situations for it, okay? But more often than not, there's a better formula to use than that. All right, so what we're going to do today, guys, is go over each one of these formulas, look at all the manipulations of the formulas, and do some sample problems on each one, okay, just so we see how they all work. Now, what I want you to do is make sure that you copy down all the examples we do, okay? Like put in the formula in your notes, like here's this formula, have your examples, okay, and do the next formula, have your examples, because I want you to get the hang of how to manipulate. What some people do, and this will come back and bite you later if you do it, is they'll write down all the manipulations on their formula sheet. Okay? If you do that, you'll never learn how to manipulate the formulas yourself. And then on the unit exam, when they give you a fresh formula sheet, you won't know how to do any of it. And I don't want that for you. Okay? So there's a little bit of algebra here. Okay? We've got to do a fair amount of manipulating of equations here. Okay? But I want you to do that manipulation rather than writing down all the manipulations instead. All right, write this one down as your first acceleration example here. I'll give you a minute to get it written down and then we'll walk through it together. Okay, first step here is to write down your givens. Acceleration problems are like the best example of why we give you a mark for doing that. You have 5 acceleration formulas to choose from. Okay, writing down your givens will help you to decide which one is best to use. All right, so in this question, it says a hybrid car with an initial velocity of 10 meters per second east. Okay, what did they just give me? They gave me VI. Okay, 10.0 meters per second east. Okay, accelerates at 3 meters per second squared east. What did they give me there? They gave me acceleration. Okay, how long will it take? What do they want me to find? Time. Okay, to reach a final velocity of 25 meters per second east. Okay, nice. Everything's east. I don't have to worry about making anything positive or negative. Everything is that way. Okay, so I'm good that way. All right, I need to find time using these 3 other givens. What formula should I use if those are my givens? Adam, which formula should I use?
Acceleration is close to final, close to velocity.
Exactly. This is the one that I have the givens for, right? I'm looking for time, and I have acceleration and the 2 velocities. It makes the most sense to use that formula. But I need to manipulate it for time. So if you were doing this on a quiz or a test, you'd get a mark for that step. And you would get a mark for selecting the correct formula. Okay? Now we need to manipulate it for t. So if I'm going to manipulate this formula for t, what do I have to do with t? Multiply it. I need it on the top. I can't solve for it if it's on the bottom. So I'm going to multiply both sides by t. All right, and then if I want t by itself, what do I have to do with a? Divide it over to the other side. Okay, so now a is over there. Okay, now I've solved for t. So generally, I would give you a mark for the manipulation / plugging in of the numbers. Okay, so now that I've got it manipulated correctly, I would simply go 25 minus 10 over 3. Okay, VF minus VI over A. Okay, so 15 over 3 should give me 5.0 seconds. Okay, so you get a mark there, mark there. Okay, so be a 4-mark question more than likely. Okay. Everybody all right with that? Okay, now let's look at all the possible manipulations of this formula here. Okay, so we already looked at how to solve for t. We just multiply t over to the other side and then bring a back over. Okay, what if I want to solve for VF? What should I move first?
T.
Yep, okay, I should move t over, okay? All right, so I multiplied both sides by t. Now what do I move? Go. Yeah, so what do I do to move it over? Add it, right. Okay, so I'm going to have VI plus t times a. All right, so now just so we understand why this works, okay, I'm just going to erase this for a second. Okay, t times a equals my change in velocity, right? If I go VF minus VI, that's the change in velocity. Everybody okay with that? Now, when I add VI over to this side, I'm saying whatever my initial velocity was, plus the change in velocity, will give me my final velocity. Okay? When I say that out loud or in my head, that makes sense. Okay? If I go to work in the morning with only $5 to my name, okay, and then I work for 8 hours, if I add the money I made in those 8 hours to the $5 I had in the morning, would I have my final pay? My final money? I would. Okay? That's all we're doing here. All right. What if I want to solve for VI? Start out the same way. Right? I got to move t first. It's not attached to VI. That's one of the rules of algebra, right? So multiply both sides by t. Okay, now, here's where there's one of two ways you can do this. A lot of people will subtract VF over to the other side. If you do that, VI is going to be what? If I just subtract VF over to this side, I'm going to go t times a minus VF equals, that negative is still there. You're going to be solving for negative VI, which as long as you remember that is fine. Okay? My problem is I'm old and I always forget. Okay? And then I get the wrong vector on my answer. So what I usually do is I do this. I add VI over to this side. Okay, now you're probably thinking, that's not getting you anywhere, Coderre. You're trying to solve for VI. Yes, I am. What am I going to do with t times a now? Subtract it over to the other side. Okay, so now VI is positive. And if I take my final velocity and I subtract the change in velocity, I should get what I started with. Okay, everybody okay with that? Up to you which way you do it. Both ways are fine. This way, when you solve it, you get the right vector, not the opposite vector. If you do it the other way, if you come out to east, the answer is actually west. Okay, so you got to watch out for that. Everybody okay with those manipulations? Okay, I would like you guys to try those two questions. Keep one thing in mind. This question gives you velocities in kilometers per hour, but it gives you an acceleration in meters per second squared. What do you need to do to the kilometers per hour? You got to convert it to meters per second by dividing by, what's the magic number? 3.6. Let me show you why. Okay. All right, if I've got, let's just say for this one here, 20 kilometers per hour, and I want to get that to meters per second, to convert the kilometers to meters, I would multiply by what number? 1,000. Okay, so there are 1,000 meters in 1 kilometer. Kilometers cancel. Okay? I also need to convert my hours to seconds. How many seconds in an hour? 60 times 60 is 3,600. There are 3,600 seconds in an hour. Okay? So I take whatever I had in kilometers per hour and I multiply it by 1,000 over 3,600. Can I reduce this down to this? Same fraction, if I do that? What's 20 times 1? 20. Okay, and then I would just divide that by 3.6. So the magic number is 3.6. Okay, if you want to convert kilometers per hour to meters per second, divide by 3.6. If you want to go the other way, multiply by 3.6. 3.6 is the magic number. Okay. All right, give you a few minutes on 1 and 2. When he comes back in.
You did. And it should be very well charged.
Yeah, I believe so, full week of charging.
Okay, let's have a look at number 1 here, guys. So on number 1, okay, it tells us that the motorcycle has an initial velocity of 6 meters per second east. Okay, so we know VI, 6.0 meters per second east. Okay, it accelerates at 4 meters per second squared east. Whoops, sorry, not VF. A. Okay, meters per second squared east. Okay, how long will it take the motorcycle, looking for time, to reach 36 meters per second east? Okay, so it's exactly the same as the first example we did. We're looking for time from this formula, VF minus VI over T. So we're going to multiply both sides by T, divide both sides by A, and plug in our numbers. So 36. Okay, minus 6 divided by 4. Okay, so when we do that, we should get 7.5 seconds for our time. Okay. Now, if you didn't get 7.5, sometimes this is what happens. People do this, they go 36 minus 6, and then they go divided by 4. Okay, that's not going to give me 7.5 because it took the 6, divided it by 4, and then subtracted that from 36 because your calculator is programmed to do order of operations. Okay, you have to outsmart it by making sure you get the top divided by the bottom. So that is 36 minus 6, close the brackets, divided by 4. Okay, you're dividing the change in velocity by the change in time, not the initial divided by the time subtracted from final. Okay, that's 2 different operations. Okay, everybody with me there? Okay, just in case you didn't get that number, if you got 34.5, that's why. Okay, it's not that you really did anything wrong other than you let your calculator take the wheel. Don't. It's a terrible driver. Okay, you got to take control. All right, how many people are done number 2? Okay, I'll give you a couple more minutes on number 2 here, and then we'll go over it. Okay, let's look at number 2 here. So first thing we got to do in number 2 is we've got to change our kilometers per hour to meters per second. So it says it's moving at 20 kilometers per hour, then it accelerates for 9.3 seconds. So is this number my initial or final velocity? It's initial. This is where I started because it says I was doing this, then I accelerated. Okay, so VI is 20 kilometers per hour, but I need that in meters per second, so I'm just quickly going to divide it by 3.6 to get my meters per second. So 5.5 repeating. Okay, meters per second, and that is north. All right, then it accelerates at 1.5 meters per second squared, north. Okay, so I've got the acceleration, okay, and it does that for 9.3 seconds. Right, what is its maximum or final velocity after that time? All right, so we're going to go A equals VF minus VI over T, and we're going to manipulate for VF. So going to multiply both sides by T, add VI, and we've got our VF. Okay, so we'll have our 5.5 plus 9.3 seconds times 1.5 meters per second squared. So that's going to give me 19.5055, okay, but that's meters per second. 5.5, okay, 19.5, I'm just going to write that for now, okay, meters per second, but it wants it in kilometers per hour. This is also north, okay, so now I just take that number and I multiply it by 3.6. Okay. We only have 2 significant digits in that question, so our final answer is 70 kilometers per hour. Okay, everybody all right with that? Okay, you would have done ones just like that in Science 10. G?
Are we supposed to square the number?
No, the units are squared, not the number.
Okay.
Right? So it's meters per second. So we say meters per second squared, but it doesn't mean I square anything mathematically. Does that make sense?
Yeah.
All right. Let's have you copy that one down as the next example here. So different formula here in a second. All right, as we're reading through this question, it says, a cattle train traveling west at 16 meters per second is brought to rest. Okay, I'm given 2 velocities in that first line. Okay, I'm given VI and I'm given VF. Okay, which one of those is VI?
16.
16, yeah. Okay, so VI is 16.0 meters per second west. Okay, and it's brought to rest. So what's VF? 0. All right, find the displacement, that's D, of the cattle train while it is coming to a stop, okay, over those 8 seconds. All right, so that's what I've got. What acceleration formula am I going to use here? Keeping in mind that it has this sentence at the end, which is kind of a hint.
D equals VI plus VF divided by 2.
Exactly, this one. D equals VF plus VI over 2 times T. Okay, that's the one that has to say it's uniformly accelerating. All right, now in this case, that acceleration is actually negative because it's slowing down. But I'm not going to have to use the acceleration here. This formula doesn't even have it. Okay, so all I'm looking for here is D. I don't even have to manipulate in this situation. I just have to plug in my numbers. So that's going to be 0 plus 16 divided by 2 times 8 seconds. All right, so 16 over 2 is 8. 8 times 8 is 64. 64 meters, which way? It was initially traveling west and it was brought to a stop. Does it ever change direction? It's only going to travel west. It's accelerating east, absolutely. But it doesn't ever go east. It slows down and comes to a stop. Okay? Everybody with me there? All right. Let's look at the possible manipulations of that formula. Okay, so we've got D equals, in brackets, VF plus VI over 2 times t. Okay, what if I wanted to solve for t? What should I do for manipulation? This is the one people have the hardest time with, but it's actually the simplest one. According to order of operations, would I do what's in brackets first? And we talked about this earlier, but really, this is just average velocity, right? If I wrote the formula like this, d equals average velocity times time, would you have any trouble manipulating that equation for t? Right? You just divide both sides by v. Well, can I just divide the whole bracket over to the other side? I absolutely can. It's just a number. It's one number, because I would calculate it before I did anything else, according to order of operations. Okay? So to get t by itself is just d divided by that whole mess of brackets. Okay? D divided by v equals t. That's all we're doing there. Okay? It looks more complex than that, but when it comes right down to it, that's all we're doing. All right, what if I wanted to solve for either one of the v's? The manipulation is the same because they're being added. Okay? What should I move first if I want to solve for either of the v's? Spencer, what should I move?
D.
Well, d's already by itself. I want to get one of these by itself. What over here can I move first?
Time.
Yeah, absolutely. I just want to move time over here, right? If I move time, does that eliminate the need for brackets? Okay, so divide both sides by t. Now t is gone. I don't need these brackets anymore. Can I isolate vf and vi pretty easily now? What do I do with the 2? Multiply it. Okay, and then I just subtract whatever one I'm not looking for. If I'm looking for VF, I subtract VI. If I'm looking for VI, I subtract VF. They're being added together. Okay, so it's actually a pretty easy formula to use. Okay, because it really is V equals D over T. It just looks more complex than that. Okay. I would like you guys to solve these 2 questions. They use that formula, so you get a little bit of practice with that formula. Okay? So on number 1, this hound is running at a velocity of 16 meters per second south, slows down uniformly, and there's that word again, okay, to a velocity of 4 meters per second south. So which one of these is VI and which one of these is VF? Not that with this formula it matters a whole lot, but which one's VI? 16 is VI, yeah. Okay, so VI is 16 meters per second south. Okay, and VF is 4 meters per second south. All right, and the time is 4 seconds. All right, so this one here, again, doesn't require any manipulation. It's just going to be 4 plus 16 divided by 4. Okay, so 20 divided by 4 should give me 5 meters. No. Oh, I forgot to multiply by time. That's why there's something missing. This is supposed to be divided by 2 and then multiplied by 4. Okay, and that will definitely give us 40 meters. Okay, and that is south. All right, questions on the first one? Okay. Then for how many people are done number 2? Okay. So a ball moves up a hill with an initial velocity of 3 meters per second. 4 seconds later, it's moving down the hill at 9 meters per second. Okay, here's where it does make a difference. Which one of these is VI? Addison, which one's VI?
3.
The 3. Okay, so VI equals positive 3.0 meters per second. VF is negative 9 meters per second. Okay, and that takes, all right, this is something I'll never do to you because it's Well, quite frankly, stupid. How many significant digits in FOUR? I have no idea, and neither do you, and there's no way to figure it out, which is why numbers should never be given as words. Okay? There'd be no way to definitively say how many significant digits this answer should have because you were given a number as a word, which would mean we would assume it was counted. So like 1 1,000, 2 1,000, 3 1,000, 4 1,000, and as a result is infinitely accurate, which is also stupid. Okay, so you will never see me give you a number as a word. Okay, we're going to write it as 4.0 here, seconds. Okay, so in this one, we're still looking for the displacement, but now direction matters. Okay, we have -9 plus 3 divided by 2, okay? And then we're multiplying that by 4. So -9 plus 3 is -6. -6 divided by 2 is -3 times 4 is -12 meters. Our answer is 12 meters downhill. Their answer is wrong. Why is their answer wrong? It's the same number. Is negative the same as downhill? It's not. It represents downhill. But the question specifically said uphill and downhill. Therefore, my answer needs to say uphill or downhill. People get caught on questions like that in acceleration problems all the time. So make note of your directions in a question because it'll come out important. All right, any questions on those ones? Okay. A couple of things. Don't pack up here, but just a couple of things so that I say them before they come on with the blessing here. Your graphing labs are due this week on Wednesday. There was in Power School, it set a different day than it did in Google Classroom. Never look at Power School for a due date. Okay? When I set up Power School, it estimates what the due date would be based on last semester. So I think it made it Saturday. They made it like the 22nd or something like that. Okay? Never look at Power School for a due date. It's never right. Okay? Always look at Google Classroom. That's where I put the actual due date. Okay? I usually change the Power School one after I notice that it's wrong. Okay? And that isn't until I set the due date for Google Classroom. So always look at Google Classroom for the due dates. Okay? March 12th is going to be your Unit 1 exam, so that's coming up. So have a look at what things do I need to ask for help on. Do I need help on vector addition? Okay, things like that. Come in and see me over the next couple weeks. Okay, because, well, we've got nothing but school for a while now. Okay? No breaks or anything like that. So make sure you come in and get help on those things if you need it. Okay? There's no shame in doing that. You are not bothering me at all by coming in to get help. Okay? It makes me feel useful and that makes me happy. Okay? So if you come in and ask questions, you're actually doing me a favor. Okay, and practice quizzes for this week. Okay, practice quizzes for this week, 4A, 5, and 6. Okay, are the ones. It's all acceleration and velocity versus time graphs and things like that. That's what will be on this Friday's quiz. Okay, yeah, and then this Thursday you'll do your vector addition assignment that I put off until, well then, I guess. That's coming up too.